quick presentation about solar weather, which is a whole field in and of itself, right? We've launched satellites that monitor the sun 24/7. There are people that specialize in this. Wasn't even a field when I was your age. But as you'll see, the solar, as I hope you're learning, the sun is a very dynamic place, and the atmosphere is very turbulent. And not only is it interesting from a scientific perspective, but it also has an effect and could potentially have a dramatic effect on the Earth. So a quick review of the three layers of the sun's atmosphere, right? So from innermost to outermost, it goes photosphere. That's the part that we can see, right? That gives it the sun its white color, so it peaks out in the middle of the color spectrum. And of course, it is emitting radiation at all frequencies, but what you see is where it peaks out, which is invisible light. And that's around 6,000 Kelvin. The chromosphere is the main part of the atmosphere, which is sometimes responsible for tinging it slightly red. And that is a little bit cooler, as you would expect. And then the big surprise is the outer edge, which is the corona. That's the only part that is visible during a solar eclipse, is super hot, And as I mentioned in the other slide, it's not completely understood, but something about the boundary conditions between the edge of the sun and the outer space. Now, I think we've already talked about this. So because it's rotating, all right, because it's a plasma, it has very strong electric and magnetic fields. And because it's rotating in a differential way, because it's not solid, that means these charges are swirling around each other, which means the magnetic field lines that go with them are swirling around, and the electric field lines are too. And it's this big mess, and you got to think about the mess is not just the physical flow and movement of the matter, that is the electrons and the charged ions that make up the plasma, but also the fields. And it turns out the fields is actually what drives the dynamic nature of it. And so these fields cause these sunspots, the solar wind, solar flares, and coronal mass ejection. So these are the four types of kind of effects of solar weather that we can, four types of solar weather that we see on the sun. So the solar wind is constant, right? This is a constant. Remember, I talked about before the atmosphere of Earth and Mars. This has already happened to Mars. It's basically like the highest energy molecules in the upper atmosphere can actually get escape velocity, and they can leave the Earth's gravity and never come back. And they can also be blasted off by this very solar wind, right? That can give them the extra energy they need to hit escape velocity. Now, the sun is the same. It, of course, is made out of charged particles, and so what you have a steady stream of emitting from the surface of the sun in all directions are charged particles, right? So electrons and protons primarily, because it is primarily made out of hydrogen, right? To the extent that there is a nucleus, a heavier nucleus, like a helium plus 2, it's a little bit harder for it to get escape velocity, right? But it's not unheard of, and certainly can happen when there's a dramatic event. But the constant outgassing of the solar wind is it's enormous because the surface of the sun is enormous, and the volume is so large, and it's estimated to be about 1 million tons per second of these single protons and electrons just streaming out constantly. And it is this solar wind, of course, that has knocked the atmosphere of Mars off of it, that gives comets their tails, and can also cause the atmosphere of Earth to glow, especially near the North and South poles when the charged particles hit the Earth's atmosphere and ionize the molecules. Sunspots, so here's a Jupiter and an Earth to scale to show you that the size of these sunspots, although they appear small on the moon, on the surface of the sun, they're frequently larger than the Earth or can be as big as Jupiter. First, these are one of the early clues that Galileo is the first person to record sunspots, was a clue that the heavens are imperfect, and also that the sun itself rotates, which, is not how people were thinking about the heavens back then. So it turns out that they usually come in pairs, and the reason for that is because they're driven by magnetic field actions. And if you remember from physics, magnetic fields always loop back on themselves. So if there's a magnetic field line that leaves the surface of the sun, it has to come back into the surface of the sun at some point. And if you watch the video after this, you will see that the magnetic field lines, although themselves are not visible, the charged particles that swirl around them are. And so the NASA has taken many, many images of in effect, you can see the magnetic field lines looping out and coming back in because of all the charged particles that are looping around it. The sunspots are cooler, but they're still super hot, right? If you're hanging out on the surface of something that is 6,000 degrees, you can be 5 or 4,000 degrees and be relatively cooler and emitting less light, and you will appear dark, and which is what's going on. And so these are places where the magnetic fields are actually coming out of the surface of the sun instead of being contained within it. And that actually causes that part of the sun to be slightly cooler and to disrupt the flow of plasma there. For reasons that are unknown, the sunspots come and go. It's driven by some internal dynamics of how the plasma swirls around during the convection and radiation layers just below the photosphere. And it peaks out every 11 years. So a solar flare is actually driven by the same mechanism that drives the sunspots. And frequently we see solar flares around times of high sunspot activity, and we see them happening near sunspots. And that is when these magnetic field lines get twisted up, right? They can, because they need to be continuous, they will twist up until a point where they snap, and then they need to get released. And at that point, you get an enormous amount of energy that gets spewed out in a certain direction in space, right? It's like all the energy that was contained in magnetic field lines and in that energy that was going out off the surface of the sun and going back in it is suddenly released. And so you get a big burst of energy, and it's super bright and tends to be higher, a lot of UV and higher frequency stuff coming out then too. And it's just an enormous amount of energy kind of released quickly, as opposed to the slower process of the radiation in the solar wind, which is constant. Right, and so you get the, it's mostly light with some particles, like, so like an extra gusty solar wind or something. The sun gets, the light, of course, takes 8 minutes to travel to Earth. It's 8 light minutes away. And then the particles, the charged particles cannot go quite as fast, but they'll be going something like 90% the speed of light, and so they get here a few minutes later. And if one of these solar flares happens to be directed towards Earth and the charged particles do hit the Earth's atmosphere, we do see its effects, right? They cause interference in radio communication, and satellites that are higher up, and the higher you get above the Earth's surface, the fewer magnetic field lines there are from Earth that are protecting you from deep space, and so the more exposure you have. And so you have to watch out for the satellites and for any astronauts that are in space, especially for any solar flare events. Coronal mass ejection is like the big behemoth, right? This is the one that we would really have to worry about. This is where the explosion on the surface of the sun is so great that it basically ejects a chunk of plasma right off the surface of the sun, right? So it's a big, huge mass rather than individual ions. It's like a cannon shot, and if it happens to reach Earth, which it has in recorded history a few times, so we figured out afterwards, none have hit Earth in recent times, but if you research this, you'll know that they have hit, and they really could take down the power grid, right? You get the most dramatic northern lights if there's the edge of a coronal mass ejection. CME hits that will send a ton of charged particles in the Earth's atmosphere and push the magnetic field lines of the Earth to more southerly latitudes from the North Pole, or north from the South Pole, and allow people in latitudes that normally can't see the northern lights to actually see them, and they'll of course be brighter and more dramatic. And this is the one that really why NASA got funding from Congress to monitor the sun all the time, because if one of these is heading for Earth, we would have time, right, because it's a large mass, so it can't travel that close to the speed of light. And we would have a time to actually shut down some satellites. There are protocols to do this, or to bring astronauts on the space station to a central location, and even to maybe shut down delicate electronics involved in the power grid regulation here on Earth to sort of protect the lives and electronics that would be at risk with the CME. Okay, that's it.